You are welcome to today's class. So we want to be looking at antiderivatives of functions. So you will recall so far that we have about how we can use tangent or velocity to discuss the derivative of function. Okay, so when we say antiderivatives, so we mean we want to use the concept of distance problems, areas, or volumes to look at or to calculate a certain area of a curve. So let us briefly explain what antiderivative is. If f prime of x is equal to f of x, okay, f prime of x means derivative of a function capital F of x, okay, then the function f of x in this case is called an antiderivative of f of x. So what do we mean by this? What you are saying in essence is that if you were given f prime of x to be 2x, for example, the slope of a certain function is 2x. Okay? So f of x in this case, okay, we should transform this, okay, to its normal curve. And of course, this will give us x squared. This will give us x squared. Then we add a certain constant to this, or okay, we'll say c, where c is an arbitrary constant. Okay, so the reason for this c is that if we have a slope 2x, there are many slope or there are many curves in which their slope is 2x. And then this c will be taking care of any constant or any arbitrary term that is added to this function. What we are seeing in essence is this. If you have a slope 2x, the function, let's say y1 equal to x squared plus 5, this curve has a slope 2x. Okay, let's see another one. This curve, whose constant here is 0, also has this as its own slope. Let's consider another curve. Let's say y3 equal to x squared minus 10. Okay, the slope of this curve is also 2x. Okay, so looking at these three curves, okay, we'll see that the constant that is added to the quadratic term here, for this is plus 5, for this is plus 0, and for this is a negative 10. Okay, so for us to choose a curve, okay, for this slope, okay, we need to add this term, which will now represent either 5, 0, or negative 10. Okay, so we just use this to explain what this arbitrary constant is. This arbitrary constant can take any of these values. Okay, it is not limited to these values alone. Okay, so there are several values that this can represent. Okay, depending on the choice of the condition given. So having said that, we have seen how antiderivative comes from a derivative of function. Okay, so now what is this antiderivative? Okay, we have said that this antiderivative, okay, is an art which we can derive from a process called integration. Integration is the art of calculating integrals, okay, and majorly they are divided into two. When we say integration or integrals are divided into two, the first one is indefinite, and the second one is the finite integral. Okay, so when we say indefinite integrals, we mean the process of evaluating a certain curve, okay, for any value or across their real line. This will be explained later. So when we say definite integrals, this is when we evaluate a certain area of a curve, okay, in a certain region. Okay, so this is otherwise known as area under a curve. Okay, so let's quickly explain these two, and then look at the difference between them. Okay, so when we're saying definite integrals, this case will have a function, but in this case we'll call it an integrand. Okay, so we'll explain this when we are about to bring some notions into the lecture. So let f of s be continuous on R. So R in this case represents the real line. Okay, and we are using R because as we have said earlier, we are about to express this f of x as a behavior on the entire R. Okay, so the indefinite integral okay, in this case is defined as the antiderivative f of x equal to f of x dx. Okay, so this is how we define indefinite integral, where this symbol is an integral sign, and the sign was introduced by this well-known mathematician called Leibniz. Okay, and that symbol connotes an elongated x. Okay, an elongated x received from because this process of integration is derived from a process called the notion introduced by Riemann, which used the method of exhaustion using some, okay, to calculate the ordinate of area under a curve. Okay, so Leibniz elongated this x, okay, to connote an integral sign, and this f of x in this case will be called an integrand, and this dx means the variable in question, okay, is x, or we say the variable of integration is x. Okay, let me come again. This sign means an integral sign, and we have said it was introduced into this study by Leibniz. F of s is an integrand, that is a term we need to integrate. Okay, anytime we see this sign, okay, before a certain integrand, okay, it means we have to integrate the entire expression here. And this z, as you can see, this z is coming from the notion of derivative. And what it means is that the variable after it means is the variable of integration. Okay, so even if you have another variable here, okay, in this case, if y is what is here, y will be the variable of integration. Okay, it means we have to integrate y in the integrand. Okay, so we are just using that to explain. Okay, so as you can see, this curve, okay, is expressed on the entire real line without limit. Now let us see what is the definite integrals. So the finite integral okay, let's take it as a finite integral. So here we say let f of x, that is the integral, be continuous on the interval a comma b. Okay, so that is this function is defined in this interval. Okay, so the finite integral of f of x is given by the antiderivative capital F of x equal to the integral f of x dx. Okay, and then when we evaluate this according to the fundamental theorem of calculus, this will be f of b minus f of a. Okay, we can get this proof from the fundamental theorem of calculus that says if a function like this is continuous in an interval, okay, so we can express this antiderivative as this. Okay, this notion here is similar to that of indefinite integral. Okay, so the only difference is that the function or the integrand, okay, is defined in a particular interval. Okay, suppose this is a curve, or this is the integrand f of x. Okay, so we have defined this portion. Okay, so this antiderivative of x is given by this area. Okay, and that is why we call the definite integral area under the curve. Okay, so where this a is the lower limit on the real line, and this b is the upper limit on the real line. Okay, so in this case, we can now talk about the difference between the indefinite integral and the definite integral. Okay, so it's simple. We can see it from the graph that the indefinite integral, the one we first explained, is a certain behavior. Okay, the process or the after expressing the integral of that form, it will give us a certain behavior or an expression of x. Okay, or a function. Okay, on the other hand, the finite integral, after the evaluation of this, okay, give us a constant or a number. Okay, because here we use this to, as we have said earlier, okay, that is mainly used to find the area or calculating the distance problem of volumes. Okay, as you can see, those terms are constant. So, but in order to get used to the method of integrations, okay, we'll first start with some integral terms or antiderivatives or functions under the indefinite integration. Okay, so and at interval, we'll be considering their corresponding definite integral as the case may be. So before we proceed, let us look at some standard antiderivatives of some integrands. Okay, so here we want to tabulate this process. Okay, where we have uh, f of x, which is an integrand, and then capital F of x, which is known as antiderivative. Okay, so it is worthy to note here that to get the antiderivative of an integrand, okay, there is no special method, okay, other than the method we have known under the derivative of functions, okay. As the word connotes, as we have said, this anti means is against the antiderivative, and as such, we refer to it as the reverse of the derivative, okay. So here we'll be introducing some terms that are already known in the antiderivative, in the derivative of functions, and then we'll be taking their reverse as a antiderivative. Okay, so the first thing we'll note here is that if you have an integrand to be 0, okay, the antiderivative will be 0, okay, plus the constant of integration, okay, the one we have explained earlier. Okay, so this will be 0 plus the constant of integration, and that will make this to be c. Okay, so don't forget we are writing this based on the indefinite integral. Indefinite integral. Okay, so let's put this. Okay, so if you have a variable x, okay, so the antiderivative of that will be x squared over 2 plus c. We have said c is a constant of integration, and that is how it will be used throughout. Okay, so now if you have a constant k, okay, I want to find the antiderivative of such. So this is if the variable of integration is x, okay, and this is a constant. Okay, so it means that there is a variable at the back of this k whose power is 0, and of course this will come this and plus c. So where k is a constant, okay, different from the constant of integration. Okay, so similarly, if you have x squared, okay, this will be x cubed over 3 plus c. So now if you now have x raised to the power of n, where n is a positive integer, okay, so the antiderivative of that will be this, okay, and so this will be the general notion of that. Okay, so this n is a positive integer. Okay, so we can use this to generalize all forms of polynomial. Okay, so similarly, let's look on to other function, the transcendental functions. Let's start from uh, bringing the function exponential x. Okay, so we'll recall that uh, under the previous studies, the slope of exponential x is exponential x. Okay, but for the arbitrariness in the function, we'll put plus c here. Okay, again, if you have a function exponential kx, where this k is already introduced constant, different from the constant of integration. Okay, so this gives this plus c. Okay, so again, if you have a function sine x, so you will recall that we'll look for a time that when we differentiate it, we have this form. Okay, and there is no other form than negative cos x plus c. So again, if you have cos x, okay, so the antiderivative of that is this. Okay, so let's continue from here. Again, if you have a sec square x, this will be tan x plus c. Okay, so let's introduce a constant to this, and let's see what it will give. So also, if you have, let's separate this. If you have sine kx, okay, so this is a negative cos kx over k plus c. Also, if you have cos kx, this is sine kx over k plus c. Okay, so again, if you have, let's consider the function that the logarithm. This is ln x. Okay. Okay. So, but one must not be confused that if you find the derivative of this, you have this. Okay. But what of when we have ln x? What is the antiderivative of ln x? Okay. So it is not 1 over x. So there are two different things. Recall, we do not see that antiderivative means the opposite of an integral. Okay. What we are saying is that it is the reverse. Okay, it is the reverse. So and as such, the antiderivative of ln x is x ln x minus x plus c. Okay, so plus c. Okay, so let's see other forms that we have. Okay, so let's go to the inverse function. By 1 over 1 plus the x squared, you recall that the antiderivative of this is this. Okay, so when you take the derivative of this is what we have. Okay, and of course, when we differentiate this, because it's a constant, it is 0. Okay, so we'll get exactly what we have here. Okay, so we have many forms of this. Okay, and then there are textbook where one can find out what are the antiderivative of some standard functions. Okay, so there are numerous of them. Okay, so we just bring about this, since there is no formal process or method of finding the derivative of function, rather than looking for the reverse of the derivative. Okay, so that said, We can now move on to some rules under the integrations. I'll be taking this one after the other. So we'll start from the sum and difference rule. So one, call this sum and difference. Or, okay, to make it different from that of, so let's say addition and subtraction property. Okay, so here we say let f of x and g of x be two integrands. Okay, by integrands, we means both of them are continuous in a given region or in a given interval. Okay, so then the integral of f of x plus or negative g of x, okay, dx. Okay, so this is similar to this. Okay, so under the sum and difference, so if you have two different functions, which relationship is either addition or subtraction, okay, so this integral sign will be distributed from them, and it is given like this. Okay, so let's consider example. If you have to integrate the function, this okay, so going by the rules that we have explained there, okay, so this means that integral this dx plus integral cos x dx. Okay, so from the standard table, the antiderivative of exponential x is exponential x, and the antiderivative of cos x is sin x. Okay, then we now put plus c. Okay, this plus c means a constant of integration, as we have earlier said. Okay, so this is the integral of this integral. Okay, so let us also see another one. Okay, for the case of a polynomial function. Okay, so we can rub off this so as to maintain the rules we have mentioned there. Okay, so also if you have to integrate the function x squared plus x cubed dx. Okay, so similarly, this means x squared dx plus integral x cubed dx. And this is equal to x cubed over 3. Okay, that is when we apply the rules under the table we showed earlier, this will be this, and this will be x to the power of 4 over 4 plus c. Okay, you see that the power will be adding 1 to the power, and the power is what is the denominator for polynomial. Okay, and as such, this will be the integral of this integrand. Okay, so that is it on addition and subtraction rule under the integration. Okay, there are several functions, or one can apply this to, especially we have only used two integrands here. but one can extend it to more than two integrands, and the rules also rules. Okay, if these are more than two integrands, this integral sign will be distributed on them as we have it for the two cases here. So let's look at another rule. This is called scalar multiplication. Okay, so again, let f of x be an integrand and alpha is any scalar, then the integral of the scalar multiplied by this is equal to this. Okay, so this alpha is a scalar. Okay, since the variable of integration is x, okay, this alpha is independent of x, and as such, this integral sign will not affect it. So that's why it is advisable to bring it out, okay, out of the integral. Okay, so the example to this is on far-fetched. If you have an integral form of this, okay, what this is saying simply is that this 2 is independent of x and can come out, and then we can have this to be this. Okay, so while the 2 is outside, one can integrate the inner term. Okay, and this is this. Okay, so this will be equal to this 2, of course, can remove a term here. And of course, this will be x to the power 4 over 2 plus c. Okay. Here, since we don't know the value for what this is, okay, so that's why we have it to be. So, one can consider another example. Let's see if you have integral of 5 exponential x dx. Okay, similarly, we can say this is this. Okay, and of course, this will be equal to the as well as on the table that the integral of exponential remains the same. This will be plus c. Okay, so that is that on scalar multiplication. Anytime we have is a scalar multiplying an integrand, okay, so it's wise for us to bring it out like this and then do the normal integration. Whatever we do there, if we factor this affects what is inside, then we do that to get the final result. So the next thing is integration by substitution. So 3. Okay, so let f of x be an integrand and f prime of x is its derivative. Okay, that is the derivative of the integrand exists. Okay, so then if you have this form of integration, okay, so that is, we have a case where the function is multiplying its derivative. Okay, so by substitution, this is this. Okay, so I'll refer to this as the integration by substitution 1 because there are two types. Okay, so there are many forms of function that look this way. Okay, and we can let's see some examples of this form. So, e.g., if you have to integrate integral x multiplied by x squared plus 3 dx. Okay, so here we'll see that this function here, okay, has a slope 2x. Okay, and because of that, we can introduce the slope of that 2x, and x appears there, so we can introduce such a slope outside there. Okay, so that we can write this as the integral 2x over x. Okay, so that if this two cancel this 2, we have x, and then we can retain this. Okay, so going by the previous, that's the condition 2 that we have. Okay, we can bring this half out in order to have this form. So this is 2x into xk plus 3 dx. Okay, so this formula looks like what we have here because the derivative of this is 2x. Okay, it's exactly 2x here. So we can now evaluate this. We can now find the antiderivative of this. Okay, one can use the quick formula straight away, and then we can also use the. Okay, so let's write this formally. Okay, so by comparison, this is f prime of x, this is f of x. Okay, the arrangement is no matter since commutativity holds under the product. Okay, so by direct approach, one can say this is x squared plus 3 squared, then over 2 plus c. And of course, because this is 1 over 2, this denominator multiply this to make it 4. Okay, so why do we call this substitution? Let's see how we are able to arrive at this. Okay, so we are going from here now. This is what the integration by substitution says that we should do, and we have done it. This is the result. Okay, but let's see what have we substituted and then what have we done. Okay, what we have actually done is this. Okay, we'll let u to be the function, okay, in the integrand. Okay, and the function is x squared plus 3. Okay, so here, if you find the derivative of u with respect to x, this is 2x, which is the slope of the, that's multiplying the term there. Okay, so what I'm trying to do here is to change on all the variables of the integration there. So this will be this implies that dx equal to du over 2x implies okay integral x squared plus 3x dx is equal to integral x multiplied by u multiplied by du over 2x. Okay, and this will be, look at this x will cancel out, and then we have 2 at the denominator. Of course, that's 1 over 2 can come out. So the remaining terms will be integral u du. Okay, now the variable of integration is now u. So it means the integral that is given here is also u. So when we integrate this, the antiderivative of this will be u squared over 2 plus c. Okay, so as you can see, if you multiply the denominator, okay, we have what is there exactly here. Then when we replace u, okay, as this, okay, we'll see that that is there. Okay, no, here we have u square, meaning this term square over 2, then 1 over 2 outside there, then the constant of integration. Okay, so that is why we got this through substitution. Okay, so let's see another example regarding this. Example 2, under the integration by substitution, if you also integrate ln x over x dx. Okay, also we can view this question here as ln x multiplied by 1 over x dx. Okay, we'll recall that if this ln x is an integrand, okay, this 1 over x is its derivative. Okay, so this compares to this. Okay, so and as such, we can get the final answer directly by saying the final answer is ln of x all squared divided by 2 plus c. That is the final answer. Okay, but let's see how we can use the substitution to get what we have just said now. So again, you say let u equal to ln x, then du dx is 1 over x. Okay, so this implies if you make this a formula, this will be du, this will be x du. Okay, because of applying by making this a formula, so this comes here, this x comes in, this comes in, so we have this. So therefore, integral ln x over x dx will be equal to integral, as you can see, you say ln x here is u and this over x multiplied by dx is given as x du. Okay, so this will be equal to, this s can cancel out, so we have integral u du. Okay, the variable of integration is now u, so if you integrate u, okay, this will be u squared at 2 plus c, and when we use this, when we replace u, this will be ln x all squared over 2 plus c. Okay, we'll now see that this ln x is our f of x. Okay, okay, that is a f of x squared over 2 plus c. Okay, so this is how we use the integration by substitution. And the one we have explained here is the first type. We have the second type of the integration by substitution, and this will be discussed in our next class. Okay, I think it's honorable to stop here. Okay, so let me just give you some exercises to work on. So we can take this for exercises. Okay, so one, so integrate the following. So two, we find the integral. Okay, so three, so we're going to integrate sine x cos x dx. And four, to integrate x x cube this is x squared plus 3x multiplied by x squared minus 4x plus 1 dx. Okay, so at your leisure time after watching the video, you can take these 4 questions as an exercise. Okay, so we have chosen them based on what we have just taught in the video. Okay, so bye for now.